we continue with our discussion on adders. If you recall, in our last lecture we looked at one kind of adder, the so called ripple carry adder, and in the ripple carry adder we looked one very distinct characteristics, that in the worst case the carry input ripples through all the stage up to the final carry output. This results in an overall worst case delay of the adder, which is proportional to the number of bits or the number of stages. So, we continue with our discussion. So, this is what I just now mentioned, that the ripple carry adder that we have seen so far, the total propagation delay in the worst case has been seen to be proportional to n, and the primary reason was the rippling effect, because you look at the full adder in any particular stage. Suppose I consider the full adder at any particular stage. Now, that full adder is unable to start the addition until or unless its carry input is available. Now, in the ripple carry adder, this carry input is coming very sequentially through a rippling effect. Because of that, the different full adders was having to wait till the carry input comes. So, the second approach or the second kind of adder that you look here is called carry look ahead adder. So, as the name implies, we are doing some kind of a look ahead to determine the values of the carries. If you can do that, then the total time complexity of the adder can reduce from order n, which is means roughly proportional to the number of stages, to order 1, which means addition can be done in constant time independent of the number of stages. But this is possible if somehow we can generate the carry bits in parallel. All the carries we generate in parallel. If you can do that, then all the full adders can carry out their additions simultaneously. Okay? They need not have to wait for the previous full adder to complete. This is the basic idea behind the carry look ahead adder. But the only trouble here is that the hardware complexity, the amount of gates that will be required, will increase rapidly with n. This is the drawback of carry look ahead adder. So, let us see the basic idea. We look at a full adder in terms of how it works. Let us consider the full adder in the ith stage of a ripple carry adder, say, where the inputs are ai, bi, ci, and the outputs are si and ci plus 1. Now, we define two different kinds of events. One we call as the carry generate event, other we call the carry propagate event. What do you mean by carry generate? Carry generate means, you see, the idea is something like this, that I have a full adder, let us say full adder of stage I. So, the inputs are ai and bi, the sum is si, input carry is ci, and the output carry is ci plus 1. Now, when I say carry generate, what do I mean by that? Carry generate means that this full adder will be generating a carry. Generating a carry means ci plus 1 will be 1 independent of what has happened in the previous stage. So, I do not care what the value of ci is. Ci can be 0, ci can be 1, whatever, it depends on the previous stages. But this ai, bi are the present inputs from the numbers which are coming. So, can we tell something from that? Well, we can at least say one thing. If ai is 1 and bi is 1, then definitely there will be a carry out. This will imply ci plus 1 will be 1. this is the scenario for carry generate. A carry is generating in the ith stage itself, irrespective of what has happened in the previous stages, right. So, this is nothing but a simple AND function. So, you see the generate function gi is defined as ai and bi. The second scenario is called carry propagate. Carry propagate is something like this. Carry propagate here you are saying is that suppose my input carry has come as 0. I am asking that under what conditions this input carry is 0 or 1. Let us say input carry has come means it is 1. It can be 0 or 1. Let us say the input carry has come as 1, which means there is an input carry. So, my question is under what condition this input carry will be propagating to the output. That means Ci plus 1 equal to 1 given Ci equal to 1. What are the conditions for that? You see, this carry will be propagated under the condition when ai is 1, bi is 0 or ai is 0, bi is 1, because you add this 1 to 1 and 0, it will generate a carry. You add this 1 to 0 and 1, it will also generate a carry. So, this condition actually talks about the exclusive OR function 1 0 or 0 1. This is nothing but exclusive OR. So, the carry propagate function we can define as ai XOR bi. So, this is what I have explained so far. gi equal to 1 represents the condition when a carry is generated in this stage itself independent of the previous stages, and propagate function will be 1 when an input carry Ci will be propagated to the output carry Ci plus 1. Now, with respect to this gi and pi subfunctions, we can write down an expression for Ci plus 1. We can write the carry output will be 1 if either a carry is generated or the propagate function is true and there was an input carry. So, if either of these two things are true, then Ci plus will be 1. So, I can simply write down the expression for this Ci plus 1 in terms of gi and pi like this. Now, this is like a recurrence relation. I am defining the carry of I plus 1 in terms of the inputs at I. So, I can recursively expand this function. Like what I can write is Ci plus 1 is gi plus pi Ci. In a similar way, the Ci I can expand as gi minus 1 plus pi minus 1 Ci minus 1. Multiply them out, it becomes like this. Again I have a Ci minus 1, expand this Ci minus 1 as gi minus 2 plus pi minus 2 Ci minus 2. Multiply them out. You continue this multiplication process till you reach C0. So, in the last term where there is C0, you will be containing the product of all the pi's. So, in general the expression of Ci plus 1 will become like this. There will be a gi, there will be in the last term a C0 with all the products of pi, and there will be several other terms. With gi minus 1 there will be a single pi, gi minus 2 there will be 2 pi's, gi minus 3 there will be 3 pi's, and so on. So, it can be expressed in the form of an expression like this. So, summation of many terms where gk multiplied by the product of pj j equal to k plus 1 to I. So, if you work this out, you will see that this expression and this generalization, they mean the same thing. So, actually I am working this out for a specific case for a 4-bit adder. Let us do it. So, let us consider a 4-bit carry look ahead adder. We are using the same expressions whatever we have written down here. So, using the same expressions, C4 can be written as G3 plus G2 P3, G1 P2 P3, G0 P1 P2 P3, C0 P0 P1 P2 P3. This actually follows from this expression. Okay, this you can check. C3 can be similarly expressed like this, C2 can be expressed like this, C1 can be expressed like this, and sum for a full adder is nothing but the XOR gate of the 3 inputs. Now, already the carry propagate function we have defined. Carry propagate function is nothing but the XOR of the inputs. So, this A0 XOR B0 I can replace by P0. Similarly, S1 I can write P1 XOR C1, S2 I can write P2 XOR C2, and so on. So, I have derived some expressions for C1, C2, C3, C4 in terms of the carry generate and carry propagate. Suppose I want to implement this, how many gates I will require? Just check. So, how many 2 input AND gates you require? This is called AND 2. AND 2 means 2 input AND gates. I need 4. Why 4? This is one 2 input AND function G2 P3, G1 P2, G0 P1 and C0 P0. I need 3 input AND gates. For 3, here there is one here, there are 3 terms, you have to do AND, one here, 3. We need one 5 input AND gate, this is one 5 input AND gate, 1, 2, 3, 4, 5. We need 2 4 input AND gate, one here and one here, and we need one 2 input OR gate for this, we need one 3 input OR gate for this, one 4 input OR gate and one 5 input OR gate, and for this sum you need 4 XOR gates. Now, in addition, you recall for generating the carry generate and carry propagate signals, you need n XOR gates and n AND gates. Now, if you do this, what you are actually gaining, let us try to understand. In a normal ripple carry adder that you have seen earlier, so the inputs were coming, carry in was there, these were the sum outputs, and the carry outputs were rippling through, right. So, if this was your input carry C0, so C1, C2, C3 and C4. Now, because of the rippling effect of the carry, this full adders, they had to wait till the carry input was available, then only it can do the computation and generate the sum. Now, you see what we are saying is that we propose to design a separate combinational circuit that will be directly generating my C1, C2, C3 and C4 values, and then I will be having 4 full adders. They will be fed with the AB inputs as usual, and the third carry input can be directly fed from here. So, you see there is no ripple effect between the full adder stages. So, after these carries are available, so these you need just an XOR function here, just an XOR function, that means just a 3 delta delay. So, when all your sum will be available, and this will be independent of the value of n. Okay. This is what we try to show in these expressions. So, if we use these expressions to generate a combinational circuit, we can directly generate C1, C2, C3, C4. Okay. And if we can do that, we can directly feed those carry inputs, so that the 4 full adders can directly, okay, we do not need the full functionality of the full adder, we need just an XOR gates to generate the sums, and this can be done in parallel, no rippling effect. Okay. So, these expressions can be simplified. You just look at one thing, this sub expressions G2, G1, P2, this one is appearing here also. If you take P3 common from these 4 terms, you will see that this same sub expression is appearing G2, G1, P2, G0, P1, P2, C0, P0, P1, P2. So, if you substitute C3 here, this expression gets simplified to C3, P3. And if you do this simplification, the advantage you gain is that, see, here you needed 3 and 3 gates and 2 and 4 gates. Here the number of gates are reducing. This AND 5 gate you do not need, and earlier you required you needed an OR 5 gate, 5 terms were ORed, but now you need a 2 input OR gate just. Okay. So, your circuit becomes simpler. So, if you simply realize these functions, your circuit will look like this. So, suppose I have my PIGI functions, then using PIGI, just following these expressions, you can generate the carries using this kind of a 2-level circuit. And you recall that Pi is nothing but the XOR of the inputs, that means one XOR gate, and Gi is nothing but the AND of the input, that means one AND gate. So, you need this much hardware. But one problem is that if we look at this recurrence relation, as the number of n increases, the complexity of this function C1, C2, C3, C4, C5, C6, they will go on increasing. So, the number of gates will also increase, the number of inputs of the gates will also increase. So, it will become increasingly difficult to implement or realize the function. So, you may know that as the number of inputs or the size of a gate increases, the delay also increases very rapidly. So, you need to control the number of inputs limited to a small value 2 or 3, let us say. Okay. So, this is one drawback. So, the circuit of this 4-bit carry look adder will overall look like this. There will be one circuit which will be generating Gi and Pi. How? Just as I have said, Gi is nothing but AND, Pi is nothing but XOR. So, how much delay will take? This XOR takes a delay of thrice delta, as I had said earlier, 3 gate delay, AND gate is a single gate delay. So, the worst case gate delay is 3 delta. Okay. So, this Gi and Pi generator requires a time of 3 delta to generate all the Gi Pi values, right. And this 4-bit carry look ahead circuit will look like this. You say this is just a 2-level AND OR circuit, simple 2-level AND OR circuit. But if you implement this like this, then your delay increases, but you implement it in the original form, the larger form, then 2-level. But here the C3 you are bringing it back. So, it becomes worst case delay of 4 for generating C4. But I am assuming the previous approach where you are not doing that simplification. So, it will be 2 delta, but using this simplification this will become 4 delta, right. And once you have done this, after this time, all the carry values are available in parallel. So, you simply do an XOR with the P values to generate the sums, and this XOR again will require 3 delta. So, you see after a constant time of 8 delta, you have generated these sum bits in parallel. So, that is why we mentioned earlier that we are aiming to reduce the addition time from order n to order 1. That means proportional to n to constant time addition, right. So, carry look ahead adder helps us in doing this. But 4-bit is too less a number. Let us say we want to design a 16-bit adder. Well, having a single 16-bit carry look ahead adder will become impractical, as I have just now said, because the expression for the carries as you go up to the higher stages will become exceedingly complex. So, the product terms will become larger in sizes, number of terms will also become very large, requiring a very large OR gates. Okay. So, one alternative may be you can have as a basic building block 4-bit carry look ahead adder modules, just like the ones we have designed. They will be taking 8 delta times for addition, and you chain them just like a ripple counter between these stages. So, this is a mix of carry look ahead and ripple carry adder. So, every 4-bit you can do in parallel, but the C4 will be generated only after, you just recall this, these carries will be are generated only after 3 delta plus 2 delta, 5 delta time. Okay. So, you will have to wait that time for the carry to be generated. Similarly, C8, similarly C12, similarly C16, right. So, unless C4 is available, you cannot start addition here. Unless C8 is available, you cannot start addition here. Well, of course, you can do this GI and PI generation in parallel, but for this carry look ahead circuit, you have to wait 2 lambda, and only after that carry look ahead circuit C4 will be generated, C8 will be generated, C12 will be generated, right. So, carry propagation between modules is still slowing down the adder here. So, what we propose? We propose that we use a second level of carry look ahead, like you see here we have 4-bit carry look ahead modules, and inside these modules we have a circuit like this. So, we already have GI PI generator and carry look ahead circuit. So, what we are saying is that at a higher level, let us have another carry look ahead circuit for which you can derive the equations in a similar way, that will be generating C4, C8, C12 and C16 in parallel in constant time. That is quite possible. Okay. So, in that case you can have a 2-level carry look ahead adder module. This is what we are saying here. Use a second level of carry look ahead mechanism to generate the input carries for the carry look ahead blocks in parallel, and this second level block will be generating the carries C4, C8, C12 and C16 together in constant time. But if n is larger, maybe you will be requiring more number of levels. Let us say I need a 64-bit adder. I built 4-bit modules, 4 such 4-bit modules I combined to build a 16-bit adder, 4 such 16-bit adders with another 4-bit carry look ahead module I can use to build a 64-bit adder. That is how so called fast adders are built in many of the recent computer systems. Okay. So, delay calculation is fairly simple. For original single level carry look ahead adder for 16-bit, the delay was 14 delta, but for 14 delta means I am talking of this circuit, because this carry generation will take 2 delta additional time because of this carry look ahead time 2 delta, because this GIPI can be generated in parallel by all the blocks. Then this 2 this time will come and it will become 14 delta if you do a calculation. But if you do this modified form, then you need only 10 delta, it will be faster. So, I am not showing the detail of this 2-level multi-level design, the conceptually the idea I have mentioned. Talking of a general k-bit adder, I am showing a quick comparison between a ripple carry adder and a carry look ahead adder with this kind of 4-bit look ahead. 4-bit look ahead means, I am just repeating once more that my idea is like this. So, I will be using carry look ahead adder 4 CLA 4 blocks, that means 4-bit carry look ahead adder. So, I use a higher level carry look ahead module for this. This will be parallelly generating these carries. Okay. So, what I have now a block which I can call as CLA 16-bit adder. So I can have 4 such blocks, 16-bit adders, and above that I can have another higher level 4-bit CLA module. So these will be generating the carry inputs for these high level adders. Okay. So in multiples of 4 I can do it. I can do it in 4 bits, then 16 bits, then 64 bits, then 256 bits, and so on. Well, means assuming that 4 is a reasonable number, beyond 4 it will be too expensive to construct a carry look ahead adder. This is our assumption. So from this calculation, the delay for a carry look adder comes like this: 6 plus 2 log n to the base 4, ceiling of that. If you make a simple calculation, it will come. The 6 comes 3 for generating Pi and Gi, and 3 for the final XOR to generate the sum, and 2 into this is for the carry generations, and this will be the number of stages, look ahead stages. If n is 64 for example, then this term is equal to 3 into 6, 6 and 6, 12. And in contrast, for a ripple carry adder, the delay, as you know, is 2n plus 1 delta. So if you compare, you see that for ripple carry adder, as n increases, the delay increases rapidly, but for carry look ahead adder, it does not increase that much appreciably. It remains more or less in the same order, 10, 12, 14. Okay, fine. Now let us look at an alternate kind of a adder called carry select adder. This is more like a philosophy which can make our addition faster. Because the hardware is quite inexpensive today, here we are using 2 adders for every addition. Let us say we use 2 ripple carry adders, and in addition we use a multiplexer. So why you are using 2 adders? Because the idea is that we do not know the input carry, let us say. So it will take some time for the input carry to be generated. So I take 2 adders. The 2 adders are parallelly adding the numbers. First one is assuming that the carry is 0, second one is assuming that the carry is 1. So we are generating the 2 sums. Later on, when the carry is known, so one of the 2 sums can be selected by using a multiplexer only after a multiplexer delay. That is quite fast. Okay. This is the basic idea. So I am showing a schematic diagram of a 4-bit carry select adder. You can see here I am assuming that it is a ripple carry adder kind of a thing, 4 full adders. There is another adder. The first one is assuming carry in is 0, second one is assuming carry in is 1. So the 2 full adders are generating the sums. The first one is this orange, this is this brown. So the 2 additions are fed to a chain of 2 to 1 multiplexers. Later on, when the actual value of key C in gets known, by that time the full adder operations are already done. So you can simply select the multiplexer and take out one of the 2 additions sums that you have calculated. Similarly, the carry out. So either you take carry out from here or carry out from here, depending on the value of C in. So this is what carry select adder means, basically, that you are trying to save time by carrying out 2 additions, one with a carry in of 0, other with a carry in of 1, and then later on you select one of the 2 sums based on the actual carry which is generated. So let us take 2 example cascades. So here we are showing how a 16-bit carry select adder can be generated by a cascade of 4 such 4-bit adders. Now in the least significant stage, you do not need a carry select adder because you know the carry in already. So there is no need of any speculation, it can be 0, it can be 1. So in the last stage there will be a single ripple carry adder, okay. But in all the other stages there will be a module like the one we have explained. Now you see, so after the addition time of a 4-bit adder is done, so all these adders are ready with their sum outputs. So this adder is also ready with its carry output. So once it is done, you select the multiplexer, take out the correct sum, select this multiplexer, take out the correct sum, select the multiplexer, take out the correct sum. So it is just a chain of multiplexers. It is quite fast. Multiplexer means maybe 2 gate delays. So the total time will be the addition time of a 4-bit adder plus the total delay of these multiplexers. After that time, you will be getting all these sum bits in parallel. Now there is an alternate way which can make the performance even better. You can make these adders of variable sizes, like the last one 2-bit, 2-bit, 3-bit, 4-bit, 5-bit. The idea is that there is no point in having all 4 bits. You see, 2 bits is the minimum time you need for this carry to propagate to this multiplexer. Now by the time this multiplexer propagates the signal, this 3-bit addition is also done. By the time this multiplexer propagates the signal, this 4-bit addition is already done. So like this, you have to make a calculation of the full adder delays and also the multiplexer delays and come up with an optimum configuration. Okay, this is a so called 2 2 3 4 5 2 2 3 4 5 configuration for a 16-bit adder. Now by optimizing the sizes of these adders, you can actually minimize the overall addition time, right? Okay. So the last kind of adder that we look at today is carry save adder. So the concept is very simple. In a carry save adder, we are adding 3 numbers together. If there are more than 3 numbers we have to add, then we have to construct a tree of such adders. Now what is a carry save adder basically? Carry save adder is basically an independent array of full adders, and only in the last stage we need a parallel adder. I will just explain. Let us take 2 examples that we want to add 2 numbers x and y. Let us say we add it twice. Here we are generating only the sum without any carry propagation, okay, independently. Like there are 3 numbers x, y, z we are adding together. So x, y, z 1 1 1 will generate a sum of 1, 1 0 0 will generate a sum of 0, independent, okay, no carry propagation. 0 1 1 0 also, and also here carry we are generating, so again independently. This 1 1 1 will generate a carry of 1, 1 0 1 will generate a carry of 1, 0 0 0 will generate a carry of 0, and so on. Later on what we do, this sum and carry which we have generated like this, we do a shift of this carry and add them up together, this sum and carry, we will be getting the final correct sum. So we are saying is that we are not unnecessarily carrying out carry propagation, we are leaving carry and sum as 2 separate words, and later on we are adding them together after proper shifting, like 1-bit shift, carry will be shifted by 1 place, we can add them together. So a carry save adder technically is just a set of independent full adders without any interconnection. Because there are 3 inputs A, B and a carry in, so technically a full adder is able to add 3 numbers x, y, z and is generating sum and carry as the outputs. So some examples I am showing here. For m equal to 3, you can use a single carry save adder to add the 3 numbers, generate the sum and carry. In the last stage you use a parallel adder to add them up to get the final sum. Let us say m equal to 4, 4 numbers you want to add, you use one carry save adder to generate to add 3 numbers, sum, carry, and the 4th number add it with this sum and carry, use a parallel adder to finally get the sum. Let us say m equal to 6, take 2 CSS in the first stage to add the 3 numbers and 3 numbers, sum, carry, use another CA to add 3 of them, again sum carry, take the fourth and bring it here, again sum carry, bring in parallel adder, you will get the final sum. So, you can have a tree of carry save adders. In the last stage you need a parallel adder. The advantage is that the total addition time can be fast and you can add many such numbers together in parallel. So, with this we come to the end of our discussion on adders. So, in our next lecture we shall be starting some discussion on the design of multipliers. Thank you.